Very good to be here. My name is Tim. I do work at Confluent. We are a company that makes a streaming data platform based on Apache Kafka. And what my team does, is we are responsible for training and documentation and soon to be online video and evangelism, things like this. So this is what my team does. Really anything developers need to be successful using Kafka or using Confluent products and to feel awesome doing it. So thank you for being here and letting me do my job. This is the most fun part of my job, is being here with you. All right, we have until 2:50, and we're going to cover some architectural patterns. They're not quite reference architectures. Usually a reference architecture is a very specific thing, like here's how you build, an example of a thing. These are more patterns or ways people build distributed systems. And these are, most of them are from real life, and I'll give examples of actual companies that use these different patterns and just kind of talk through each one. Now, if you were in my earlier talk 2 hours ago, you will see some overlap. So I want to warn you right now, if seeing a few of the same slides will make you angry, you want to begin processing that anger now. Ideally, it won't make you angry at all, but just so you know, there's a little bit of overlap. Otherwise, they're fairly different talks that do different things. Normally, I would say if you have a question, ask it, but we're in a little bit of a large space here. So if you're really loud, shoot a flare in the air and then ask your question. Otherwise, just see me later. I'll be around all day, today and tomorrow. All right, let's look at the architectures themselves. We're going to look at four different architectures for building distributed systems. Look at the pluses, the minuses, who uses them, why, and I'm going to try to come up with a rating of them when we're done. All right, we'll begin with what I call the modern three-tier architecture. Now, when I was a younger developer, I entered the world of Java in about 1999 or 2000. Before that, I had been writing firmware. So with my usual impeccable timing, just about the time the first .com bubble was over, I said, hey, let me get on board with that internet thing. I became a Java developer, and people were talking about three-tier architecture back then. And it like, cutting out here, hope we're all right. It looked like this. You had at your front the presentation tier, in the middle what we called the business tier. I'm glad we don't usually use that term much anymore. And then on the back, the data tier. Pardon me just a moment. That has a terrible word on it that it shouldn't have. There was, just before this talk, a terrible crisis in the formatting of this entire slide deck, and that crisis is just about over now. So back in the day, the presentation tier was JSP. In the middle, we had terrible things that I shouldn't even say in polite company, and on the back end, another terrible thing that I shouldn't even say in polite company. This is just how we built. These weren't really distributed systems as such back then. They didn't really act like it. And a few things went wrong with that, right? And those things changed over time. And it felt like this, we talked like this went away. And in the middle of the 2000s, there in the Java world, there was struts and Spring MVC, and then Rails happened, and we were very focused on these MVC frameworks, and we stopped talking about tiers. And if we look now at how you might build a comparable system, I'm going to keep the diagram the same. I'm going to take away the screaming people, and I'm going to change the labels, and you might build this. You might have a React front end and a Node.js middle tier, and you might, for purposes of scale, have Cassandra on the back end. Now, that would be a perfectly respectable system, and people do this, and it's no different than 15 years ago and almost 20 years ago, the three-tier systems we were building. Really is the same thing. So let's talk about how to scale this. Now, the front end, just now as then, scales automatically. We have lots and lots of clients, lots of browsers out there scaling the front end. And we've gotten a little smarter, I think, in that we are pushing more and more application functionality into that front end with the 600 JavaScript frameworks that exist for the front end, a lot more of the application lives out front than it used to. So that now is going to come into some kind of a load balancer. That'll be Elastic Load Balancer if you have asked Amazon into your heart and you do everything in Amazon, or it'll be some species of Nginx if not. And then we simply have lots of node instances. So this would be a typical way of doing it. And again, this is indistinguishable from what we might have called three-tier in the days of yore a long time ago. On the back end, since the database was initially very expensive, and then when open source databases became popular, the database became a pain point of scalability. What do we do now? Well, we usually will just have a Cassandra instance that's a good way to accomplish that back end. Like that database problem, if what you want is a system with a database where you update things in place, that problem feels more or less solved. And we can just split that into 3 pieces like so. Now, for each one of these architectures, just to make this worth our money, I want to pick a technology to explain a little bit of, so you have some idea of where the magic is. Here, without making it a Node talk or a React talk, I don't really want to get into those. I kind of want to talk about a distributed systems technology in each one. So we're going to focus on Cassandra. I want to talk about Cassandra for just a few minutes. Super duper lightweight introduction to Cassandra. And as I said, if you were in my earlier talk, you got this same lightweight introduction to Cassandra. But if it was your first time, you probably need it twice. Now, Cassandra database is not a terribly difficult thing to understand. The nice thing about it, and the thing that originally, 6 years ago when I first started looking at Cassandra, the thing that won my heart was all of the nodes are the same. You only need one shape and one color to draw the diagram. Just make a box, and that's all you've got. It's an entirely peer-to-peer database. There is no central node of any kind, and I really, really like that. Each node, though, has a unique token, and we use those tokens to divide up the data that we're going to write and read in this database. Because the problem is, once I scale my database from being able to put all the data in one place to now needing, in this case, 8 nodes, in large clusters, a few hundred nodes, I need to know, if I'm going to write something, where do I write it? And so we assign each node a unique token, and we always, by convention, we draw them in a circle. We draw this as a ring of these token IDs. Now, this is not Cassandra talk. I only have about 5 minutes to talk about Cassandra here, so I'm going to skip over some details. In particular, I'm not going to say anything about the Cassandra data model. It's not a key-value database, but I'm about to treat it like one, because that's an easy way to begin explaining it. So, with that, we're going to act like Cassandra is a key-value store, and I'm going to say, hey, I'm going to write a key-value pair into this, in this case, the name of my favorite coffee. And I think I'm a really boring coffee drinker. This is true. Probably 90% of the coffees I order, just an Americano. I'm a simple guy. So Tim here is the key. Americano is the value. That's my favorite coffee. And if I want to write that key value pair to this cluster, what we'll do is we'll run the key through a hash function. And in this case, I'm using, this is the 16-bit Arduino version of Cassandra, because those numbers fit on the slide better. Rather than the real 64-bit numbers. Those are a little unwieldy. So we hash that, and we say, okay, 9F72. And I look around my cluster, and I say, well, that's bigger than 8,000, less than A,000. That means that A,000 node has got responsibility for that token. And if I'm only writing a single replica, which would be a little crazy in production, there you go. I write that to that token, and I'm done. Now, later on, when I go to read Tim's favorite coffee, as a client, I'm ignorant of where that is, right? Nobody's going to remember what node that got written to. So what I do, if I want to read the Tim key, is I'm going to do the same thing. Hash that key, look around the cluster, say what node in this cluster has responsibility for that token, and that's going to be the range of 8,000, 8,000. So I can look there, pull it out, and I've read Tim's favorite coffee. We're ready to proceed with the order in this web scale coffee shop. Now, obviously, I wouldn't want to write just one copy, right? Because one of the things in a distributed system is you're using lots and lots of computers. You want lots and lots of uptime. You're always going to assume that some node is going to be failing at some time. That's just good sense. So, for example, in a simple case, I might, instead of just writing to that node, I'll just keep walking around the cluster to the next 2 nodes and write replicas there. Now I've made 3 copies of the data, and I can lose nodes and still win. Now, this itself seems elegant and simple, and it's kind of easy to wrap your mind around. Where does the complexity emerge here? Well, once I have taken mutable data and copied it in 3 places, bad things happen, right? That's a terrible idea, because what if when I go to write it, one of those is having a long GC pause or something, and the write doesn't work? One of those nodes, like today, my favorite coffee is an Americano. Tomorrow, I might change my mind to almond milk latte, which is kind of my 10% jam. And the update tomorrow, maybe one of the nodes won't get written. I have to manage consistency now. Cassandra has all kinds of elegant answers to how that works, which we won't go into in detail here because there's other things to talk about. But that's a typical pattern. Anytime you're doing something that would have been simple on one server, when you do it on many, you fix a problem, you create 5 others. So that's a complexity. Cassandra's answers to consistency are really fascinating. I love the way it handles those problems. And there's a cool website called DataStax Academy, if you're ever interested in more of this, academy.datastax.com. I don't work there anymore, so I can plug it as shamelessly as I want. Now, the really shameful part about that is there are a lot of videos of me on there, so maybe this is just more self-promotion, and I just can't stop myself. But for more info on Cassandra, lots of free resources there. I'm back? Okay. I'm cutting out occasionally, so if I cut out for long, we'll fix it. Strengths of the modern 3-tier architecture. 3 things. Lots of rich options on the front end now. You can make the front end very responsive, put lots of functionality out there. The more compute you can push into the front end, the better you scale, right? Because you've got thousands, maybe if you're successful, millions of computers doing that work for you. So any compute you can push into the front end and still like the way your app is built, you have won. You've distributed that work to the front end, and lots of good options there. The middle tier, these days, not super hard to scale. I remember in the early days of Java frameworks like Struts and Spring MVC, people would worry about, oh no, I've used the HTTP session too much, and it's hard to cluster Tomcat and all these things. For the most part, we're better at that now, and the default way of scaling the middle tier is easier, so that's a good thing. Also, the data tier, with databases like Cassandra now kind of being fairly well battle-tested and well available, and it's pretty easy to find people who have used them, that's getting to be a safe choice. You've got a very scalable data tier. As an example of somebody who has productized part of this, Walmart. Walmart, gigantic US and I guess global retailer, has taken their version of React and Node.js and packaged them as a project called Electrode. So if you remember, those are just the 2 examples I happened to pick, presentation tier and middle tier. Well, large operations are using them and even productizing frameworks based on them. So there you have it. Now, sorry about that. What's bad about this? Any state that exists in the middle tier is going to be an impediment to scaling that middle tier. So you have to write those middle tier servers in a way that's stateless, which means all they know is what they get in the request and what they can learn from the database. And that is, of course, harder than it sounds. That's an easier thing. It's an easy thing to say, but actually doing that and delivering low latency request times is a challenge. So that can be a bit of a problem. Let's rate this. Now, for each of these approaches, I'm rating them on scalability, difficulty, and flexibility. Now, I thought hipness is a little strange. I was originally thinking maybe like maturity would be a good way to do that, but maturity and hipness I'm viewing as inverses of one another, and I picked hipness. I'm going to say modern 3-tier is a 4 out of 5 on scalability. Most of it, as long as we're responsible with our middle tier, it's actually a pretty dang scalable framework. Hipness, we get 2 out of 5 beards. It's not especially cool, but it basically does work. And difficulty, 3 out of 5. Most of these pieces are becoming pretty easy to deal with. Cassandra can be a little tough for new people, but clustering Node and putting React on the front end, if those are the tools you happen to choose, you can fill in those blanks any way you want. That stuff's getting fairly easy. And again, you can probably build anything with this. So this is not a bad approach. Not a bad approach at all. And Walmart.com, like I said, that's a gigantic global retail site built this way. All right, let's talk about the next pattern, the sharded architecture. A slightly different approach. We'll start with this same basic diagram here. We've got our client on the front, we've got a database on the back, and a piece of complete application in the middle. And at low scale, you build the system like this. This works. There is some number of clients. There's one server that's being the complete application. There's this one Postgres server on the back end, and you back that up in some way that you're happy with, and life is great. You're not building a distributed system. Like, everything is beautiful here. And if you could just live here, if you take my advice and just never leave this slide right here, your life is going to be so much better. As I said, if you were in my last talk, I took some time to try to talk everybody out of doing anything with distributed systems. It's terrible anytime you do. Everything goes wrong. But you're here, which means you're not going to take my word for that. If you would just live here, life would be great. But what's going to happen? At some point, maybe the application, the site, the business, whatever it is going to have some success. There'll be too many clients for that one application and that one database instance to handle. So what do? Well, the fundamental insight of the sharded pattern is to say, we're going to break the application up into pieces such that each one behaves like a non-distributed system. You remember my advice, don't build distributed systems. Well, the sharded pattern really tries to live that way. It says, I'm just going to have a complete application instance, a chunk of the whole application, and just repeat lots of those. And in between my clients and those chunks of application, I'm going to have some sort of router that will direct traffic from the clients to the correct shard. And this gets done. Slack is a good example of a very successful modern service that's built with shards. It's essentially a sharded application. Easy enough, easy to think about. That router could be a little bit of a trick, but it's not all that hard to do. And if you're a service like Slack, where the whole universe of Slack is broken up into these organizations, and most of the organizations are not that big. For example, my family Slack channel, houseofberglund.slack.com, unless you live in my house or are one of my children, you can't come, so I regret that I can't. But houseofberglund.slack.com, very small Slack org. It's going to fit nicely into a shard. And frankly, it will be able to share server resources with a number of other small Slack teams too. So this is really, really well. Now, when does this go south? Let's talk about when sharding goes wrong. Now, just thinking about the sharding of a database for a moment. Not a whole application, but sharding of a database, time-tested pattern that is nevertheless fairly bad. We'll have, when we begin scaling the database, we usually start off with read replicas, like you show here. The one big database there, that's the master. All the writes go to that, and we replicate those to the read slaves. We can direct reads from the application to those slaves, writes to the master, and everything's okay. Usually, there's probably a little zookeeper down there, just kind of doing its thing, helping us coordinate something or other. But when we run out of gas with this is not sharding yet, this is just read replication. When I've got too much write traffic for that master to handle, well, now I have to break up the database into chunks or shards and direct traffic to each one of those shards based on some key. Now again, if you're Slack and there's always an organization that you're connected to, this works great. There's always a key to start with. And so you can conceivably shard. So there are workloads like that that are very shardable. There are other workloads that are not as shardable. So this works sometimes, sometimes it doesn't. But suppose it works, suppose we're Slack and this is working out well. Let's look at what can go wrong. Here's where sharding a database at least can really get ugly. Now, remember that zookeeper down in the corner? He's helping do things like elect a master. Each one of those shards has 4 servers in it. One of them gets to be the master. Only one of them gets to be the master at any time. That's where all the write traffic goes, and you can load balance the reads to the slaves, and life is good. But bad things happen in networks, and some of these servers might occasionally get cut off from the other ones. We call that a partition. A network partition is when one or more of the servers in your cluster can't talk to the others. This can be for very simple reasons. Like I said, a GC pause. Some people define a long GC pause as a partition. Sometimes networking infrastructure can get misconfigured. Ports can break. Switches can break. Anything can go wrong. Sharks can bite cables. Whatever it is, we can get a partition. And when that happens, well, what's going to happen? Those guys are going to go, oh no, the master is dead on the bottom side of this partition. They're going to go talk to Zookeeper and say, oh, the master is dead, and we need to elect a new master. And that's fine. And then later on, the partition will go away. And what happens then? Well, this is, I guess, kind of like in European history, we have the Avignon papacy, where you had a pope in France and a pope in Rome, and both of them claimed to be pope, and they were anathematizing each other, and it was very, very messy, and it took a long time to sort out. That was not a partition-tolerant system. It was hard to resolve the partition. So that happens in sharded databases, and in other kinds of sharded systems, that's a potential weakness. Also, typically in sharded systems, you have to decide up front how many shards you're going to have. It can be difficult to reshard later on. Now, that's not universally true of everything. There are like some databases that will help you reshard dynamically, but it's a thing that requires a certain amount of planning ahead and can have problems in production. So, what is sharding good at? Sharding, again, lets you pretend that you're not building a distributed system. Each chunk of application functionality you build conventionally using known and ideally simple technologies. It's also easy to isolate one client from another. So if you've got, depending on your physical networking topology, geographically where clients are served can matter a lot. There are, for example, I don't know of all the countries in Europe, but I know German data privacy laws don't allow German companies to host customer data on US servers. So if you have infrastructure that's located in the territorial United States, a sharded system might let you locate some of that other infrastructure in other areas where data sovereignty laws are compliant with whoever has the guns locally. So that's potentially a strength there. It's easy to isolate clients from one another in terms of data and in terms of where things are deployed. Where does this go wrong? Now, It feels like a good way to manage complexity, and it is in terms of the application. And as long as most of your effort is in the application itself, you've done a good job keeping the distributed system bad stuff away from you and just really acting like you're building an application for a single server. However, little bits of complexity are going to nose their way back into your system. For example, monitoring and logging. You pretend that it's not a distributed system, but we all know that it is. And if you're running a large sharded system, you are going to need to know what's going on all of your shards, and you're going to need to know aggregate performance data. There's going to be trends that are important to you. So monitoring and logging, still distributed concerns. You are not getting away from that altogether. Also, there's complexity in the router, right? The router is a new piece of infrastructure that needs to be developed. It's not that bad, but that's going to be another little piece of things that you have to do. In terms of the data itself, I now have as many databases as I have shards, and that's potentially a lot. And if I want comprehensive analysis of all of that data, I'm going to have to do something like ETL to take my 6,000 sharded databases and squish them into one place so I can do analysis on that data. So I've probably created the need for some kind of ETL process that I would otherwise like to avoid. Oversized shards are also more or less a fatal problem. Other problems, like what we saw with master election, or as I call it, the Avignon papacy problem, those we can figure out ways to solve those. But if one shard becomes larger than I can handle on the hardware that I deploy, my approach has failed. And I will now need to introduce more conventional distribution techniques inside that shard, like we saw with the modern 3-tier. A shard becomes its own, a shard suddenly becomes its own little distributed system. We're going to get through this. And like I said, you need to be sure that you're never going to have a shard that's oversized. That's a bad thing. So what we often end up doing to solve the data problem is we might take that data on the back end and aggregate it into a large database for analysis or logging or something like that. So in other words, we've pushed a lot of the distributed system stuff away, but it's always going to creep back in. That abstraction is always going to leak. You never get away from it altogether. All right, now let's rate this guy. I'm going to give it a 3 out of 5 for scalability. Scales just fine, as long as your shards don't get too big. It's not very cool, but that's okay. Sometimes not cool is the best. It has difficulty in surprising ways because of what it forces you to do for analytics, in that it forces you to deploy some kind of ETL solution, and other cross-cutting concerns are still always a part of your life. It's fairly flexible. It's not too bad. All right. Well, Lambda is not a general purpose architecture, but it's more of a way of dealing with analysis. And it introduces one really interesting topic and lets us introduce another open source project that's worth talking about. So I like bringing it up. Also, it's a great springboard into the fourth and final architecture that I want to talk about, which is streaming. So Lambda kind of tees us up nicely for that. Lambda makes this distinction between what we call streaming data and batch data. Now what's the difference between streaming and batch? The difference between streaming and batch is batch data processing is what we do on data that lives somewhere. It's in a database, it's in a file, it has come to rest in some place, and we address it by that place that it is in. Either a file name and an offset, or a primary key in a table or something like that. It is in a place somewhere. Streaming data is a log of events. We might also refer to these by the terms bounded or unbounded. Bounded data is batch data. We sort of know how much there is. It's right here. We can look. Unbounded data is just a succession of events that are happening, and we presume they'll never stop. Last year, I think it was about a year ago, coming up on a year ago, there was a great interview on Software Engineering Daily with Frances Perry. Now, she's a lead of the Apache Beam project, which is one of the kind of streaming data options out in the world right now. And if you're not a Software Engineering Daily listener, you should be. It's a terrific podcast. It's an incredible amount of work being done there just to keep developers up to date on what's going on in the world. I'm constantly impressed with this thing. And Perry happens to be an extra good guest. I've been on Software Engineering Daily, and I've been interviewed a number of times. I learned a lot just from her media presence. She did just a great job. Good on the content, good on the delivery. So I recommend that podcast if you are interested in the topic. So the Lambda architecture assumes unbounded data. There's a stream of stuff happening, and it assumes that the data is immutable. So these are events, and events are, after all, immutable. Once something happens, and I have a record of the thing happening, I don't want to change that record. Events are definitely immutable, and sometimes we're painfully aware of that, right? You can't go back and change something you did. So Lambda's on board with that. We have unbounded, immutable data, and let's talk about what happens. So we've got these events in the world, and on the one hand, we're going to write those events to a database. This is term storage, and this is we could say Cassandra, we could say we're scaling a relational database somehow, but this is for our bounded analysis. We're going to have some batch framework, like a Spark, or I'll just stop there, hopefully it's just Spark, and we'll do that batch analysis on that data at rest in that database with relatively high latency. Spark is a faster framework than Hadoop MapReduce is, but usually with a Spark job, you're talking about a long time. Seconds at the least, minutes, hours are not impossible if there's a huge amount of data and you're doing something complex. This is high latency analysis on lots and lots of data. Those events also get written into some kind of event processing system. The Lambda architecture thinks of this as a temporary queue, some message queue of unbounded events, so they get written in and then expired after a relatively short period of time, so we can do this low latency analysis down here. And we're going to take both of those, our high latency bounded analysis, our low latency unbounded analysis, and write those results to some kind of scalable database on the back end. So anything we need to know now, like Twitter, for example, the notification, your two friends just liked this tweet. I assume some of you may get those notifications on your phone. I'm not convinced of the value of them, and maybe I should turn them off for myself. But that's a real-time breaking news kind of thing. That's going to be in that event path down at the bottom. Longer-term analysis might be like what business analysts are doing about what people respond to what kind of ads and ad hoc querying or that kind of thing. Those would be batch jobs running on that top thing. So the event queue coming in, usually people think of that being Kafka. We'll say Cassandra and Spark for the batch analysis, some kind of event processing framework. We'll talk about options in a minute on the bottom, and then those things get written to a low latency scalable database on the back end like Cassandra. So that's the idea of the Lambda architecture. The basic insight is there's two things you want to do, and it's hard to do both at once, we think, and so let's build two systems and optimize one to doing the unbounded analysis and optimize the other to do the bounded analysis, and just write all the code twice. We'll come back to that. This brings us to another open source project we can explore a little bit, and that is Apache Kafka, since you've usually got a Kafka in a Lambda architecture. After we go through this, we'll peel back the layers on Kafka a little bit more and see if we can simplify Lambda and arrive at our fourth and final pattern. All right. In Kafka, we've got producers, consumers, and topics. Topics are just named queues of messages. A topic has a name, I put messages into it. As a producer, as a consumer, I take messages out of it. A topic lives on a broker. A broker is just a server running Kafka. So it's a computer running Kafka. A topic, importantly, can also be partitioned, because probably that one topic, since we're in distributed systems land, is going to get too big for one machine. Either there's going to be too much data, or the data is going to be changing too quickly. I'm going to be reading messages in and writing messages out at a rate greater than one machine can handle. And if I do that many, many times with lots and lots of topics that get large, I'm going to need a cluster of brokers that are all working together. Let me give you an idea of how partitioning works in Kafka. Now, if I were leading a simple life and using a non-distributed message queue, I would probably still have topics, I would certainly still have messages, producers would put messages into topics, consumers would take messages out of topics, and I would have guaranteed ordering. Anything I put in, I would get out in the right order, and life would be great. Now, life is still pretty dang great with Kafka, but I have to give up one thing, and that's ordering. So, let's say instead of just one partition, I want to partition into 3 brokers. I want 3 brokers to cooperate in handling this topic. So 0, 1, and 2 are 3 separate computers. I've got my producers over here on the right, I've got my consumers on the left, and my producers will just start to make messages. Now, each message, we're going to look at some portion of the message and hash that. Like maybe look in and find an account ID or an IP address or some sensor ID or something like that, and hash that thing. And using that hash, I'll figure out which partition I write to. So different messages that get produced will get written to different topics. And we see already we've forgotten what the overall order is. I don't have overall order. I only have order within partitions. And that's a fundamental limitation. Once I decide to be a distributed message queue, I'm not really going to be able to have global ordering. I'm only going to be able to have ordering within each partition. And that's a bummer. That's a thing I have to give up on, but I deal with it. And because the producer is able to decide what part of the message gets hashed, if it wants to be thoughtful about that, then I can have ordering, say, within username or within IP or within sensor ID or whatever my domain is. I get to preserve some ordering. Partitions are ordered, whole topics are not ordered. So then as I consume, those consumers will read messages out in order. And of course, those consumers, it doesn't show in the slide, but those consumers are running in parallel. All right, that's just a quick peek into Kafka. Kafka's usually involved in Lambda, and it's definitely going to be involved in streaming, as we'll see next. All right, what are the strengths of Lambda? Well, again, its basic insight is to say, look, we want to do batch jobs and we want to do stream analysis, and it's real hard to do both of those at once. They're just different kinds of systems, and they deploy differently and you optimize differently, so let's just build them both and optimize both at both tasks. That's its basic strength is we get these 2 subsystems and let's try to be good at both things separately. It's also good at unbounded data, and the previous 2 architectures are not good at that. The weakness, you have to write all the code twice. That's basically the classical approach to Lambda. This is becoming an almost frowned upon thing because it's hard. People's experience is, well, I have to do this stuff twice. And that is not fun to write basically the same code in 2 places. So let's rate this. Scalability, very scalable. Definitely only 1 beard out of 5 at this point because it's a 5 out of 5 on difficulty. And it is not really a general purpose framework. This is for analysis purposes. You wouldn't build your whole site using Lambda. You'd analyze events using Lambda. But this brings us to streaming, our fourth and final architecture. Now, in streaming, we have a few things that are true. Usually people get into this starting with integration as a gateway drug. I have system A and system B, and they need to talk. Even if you're not building a Lambda architecture, a lot of people these days are starting with Kafka to integrate systems. I've got data I need to load into Hadoop, or I've got microservices and I want them to be able to exchange messages with one another. Good. Another fundamental insight of the streaming pattern. Databases are, by their nature, static things. That means, what a database means is I've got something that's true and I'm putting it here, and I'm going to be able to address it in this place. That data just sits there. The business that you build around that database, well, it's fundamentally a dynamic thing. There are events happening and things changing all the time. So what we do, a lot of what we do, frankly, a depressing amount of what we do as developers is we take form submissions and we do a little processing and we write things to a database. And then later on we read things out of a database and do a little processing and format it and send it back to a client. It's kind of your job, but it's important work. Don't get depressed. The point is, the mapping of these events onto the static data is a little bit of an impedance mismatch. And streaming says, hey, wait, because the world is dynamic, maybe the system should be too. The Kafka approach to streaming, which we're going to see, keeps computation very close to, keeps stream computation very close to where your application code is. This is absolutely key. That doesn't make sense yet, but it will. Keep that in mind. You want to keep stream computation very close to your application. All right, let's look at these concerns one at a time. Integration usually starts off with, hey, I've got this database, and I've got this application, I've got this other application, and they'll both talk to the database, and they'll occasionally write stuff to my HDFS cluster, and everything's fine, and then you build another application, and there's another database, and a Elasticsearch, and more services, and everything. It's pretty soon it's, it's bad. Bad things have happened, and these applications are talking to one another. That rat's nest in the middle, we can clean up if we decide, hey, look, all of the services will always just exchange messages with one another. These messages will go into a common message bus, and we'll leave it at that. Now, if you've been around for a while, you recognize that pitch from about 15 years ago. That sounds like the pitch for an enterprise service bus. You have all these disparate services in your enterprise. Let's have them all read and write XML messages into this expensive service bus, and all your problems will be solved. And oh, by the way, let's put some message routing and processing functionality up in that service bus and pay an enterprise software vendor lots of money, and everything will be fine. And usually back then, the CIO bought the software on the golf course, and we just were the beneficiaries of the decision. Make sure I don't sell you that here. So in the next few minutes, I'll try to explain why streaming is different from that. What we end up with is, rather than that rat's nest, we'll have a message bus at the middle, and we'll have a service here and a service there, and we'll have monitoring, we'll have an Elasticsearch cluster, we'll have some analytics, we'll have Hadoop. All of those things are fine, and this is basically describing a microservices implementation here. All of the services are just going to exchange messages with one another, rather than necessarily writing to a database. One service writes to a database and to integrate through there. The services will simply read their inputs from topics, write their processed outputs back to topics, which will allow other services to consume those same things. So there isn't ever really a central database where these things live. There are just topics. We just stream data. And those connections there, in the case of Kafka, those often end up being very standard things that you want to do. Like, it's very typical to dump data into an Elasticsearch cluster or into Hadoop, or maybe you've got a legacy database out there somewhere and you want to read data from that database. Those lines can actually be implemented in modern Kafka. Modern Kafka is much more than just a message queue. When you're building a streaming system, modern Kafka's got a thing called Kafka Connect. That's an API for doing those standard connections to things on either side of the message bus. You don't always have to write that producer and consumer code yourself. Often, if you're connecting to a standard thing, it's a configurable item and not a thing you write code for. The event stream. I was kind of waving my hands and saying, here are these events coming from out in the world. And yeah, fine, you say, Tim, as long as you've got an event-driven system, that sounds great. But what if I've got a database? What if I've got, a record of truth somewhere? Well, the translation between database and stream, or table and stream, is a little easier than you might think. Updates that I make to that database, if I insert a new row, well, that's an event. If I change a row, well, that's an event. If I delete a row, that's an event. So I'm able to take my, basically create a change log of what happens in my database and make that a topic of events. Databases do this internally all the time anyway. This is a standard thing. So if you've got a table and you need to translate that at the streaming world, it's okay. And doing that, starting to rely on my message queue as a place to store data, isn't as crazy as it sounds. The retention policy in Kafka is 7 days by default. The New York Times stores all of its newspaper data, going back to the 1860s, which is a long time ago if you're an American, in Kafka topics. So that retention policy is configurable. You've also got great I/O performance. You've got very fast writes. Anything you'd want in a distributed database, partitioning, replication, scale, those things are all there. Next insight that streaming asks us, next change streaming asks us to make. Remember this. We've got the 3-tier architecture. We've got the presentation tier, the business tier, the data tier. What we normally do is we make a request to the presentation tier, and then we get a response. Well, in a streaming system, an event happens to the system, gets consumed. Another event happens to the system, gets consumed. Maybe it gets consumed by a service, gets written to Elastic, gets written to the analytics system. Whatever has to happen in there, we're able to do that. The events just come in, each service is able to consume them the way it wants. Then later on, I can go to a particular small-scale, well-defined service. I can make a request of it. I can make a request of my Elastic cluster and get a response from it. All of which gets us finally to something that this talk is not about, but I strongly recommend you check out, the Streams API for Kafka. This has been a core part of Kafka since a year ago. On streaming data, it lets me do aggregation, filtering, it lets me join certain types of streams, and it doesn't require its own cluster. This is not like Spark or Flink or one of those things where I stand up a streaming cluster. This is stream processing that lives inside my service. So deploying this is super easy. I already know how to deploy my services, so my stream processing code just gets deployed along with them. Finally, let's rate this guy. Overall, we'll give it a 5 out of 5 for scalability because, well, it can scale very well. Very hip. This is the leading edge architecture of these 4 in terms of mind share. It's kind of hard to do because it requires a lot of different thinking, but you can build any kind of system with it. Highly flexible. Now, with that, we are just about at time. Can we really declare one winner? We cannot. This is a little bit of a salad bar kind of thing. People are going to pick what they want. There are different architectures that are suitable for different purposes, and that is about the best we can say. All of these decisions are always contextual. Let me give you a few things in closing. In fact, this is the one you want to take a picture of. Since I'm with these guys, if you want to know more about streaming and more about Kafka, check this out. You can find out about our meetups, join our Slack community. I would love to see you there and hope to see you at a future meetup. Also, Summit in San Francisco. Talk to me if you want a discount code. I can hook you up. I'll be hanging around later. You're out of here. Time's up. Guys, thank you.